Welcome you to the last colloquium of this spring. Welcome, everybody. And today's speaker, whom I will introduce in a second, is Åsa Farhagen from the Technical University in Denmark. She has done her PhD actually in pure mathematics, differential topology, if I understand correctly. I had to look at your thesis, and that's what I got from it. So actually a pure math education in Helsinki, and finished her PhD officially 2010, but in 2009 she already handed in, which made it possible that right after the PhD she went into like machine learning and analysis of data of structures with computers, data analysis, one should say. So she did a postdoc at the University of Copenhagen, followed by a position in Tübingen at the MPI for intelligent systems and the developmental biology MPI. They had a group at the two MPIs together, and shortly after, in 2014, returned to Copenhagen as an associate professor at the University of Copenhagen. And 5 years later, she became full professor at the place where she is now, the Technical University, where she's leading a group in medical imaging. And today, it's a great pleasure to follow her talk on predicting graphs. Please.
Can you hear me now? Yes. So thank you, Sven, for the very nice introduction and also for the invitation to come here and give a talk. Like Sven mentioned, my training is in pure maths, but since 2009, I've been working at the intersection of math, geometry, and machine learning and medical imaging. And this is a field that's been changing a lot over the last 10 years, where we've been moving from perhaps relatively simple machine learning models to today, deep learning models. And maybe in the talk, you'll also see a bit of this journey. Please, if you have questions during the talk, don't hesitate to ask them. I mean, I don't want to talk if you're not following. So just go ahead and ask if there's anything. My talk is about graphs, and graphs, they're everywhere. In the picture, you see on the top left an example of a scene from computer vision, where one way to understand scenes is to detect objects in the scene, look at how they relate to each other, and one way to look at how they relate is by representing them in a graph. You see some examples from chemistry and biology with a molecule in the bottom row or the protein upstairs, which they're also often represented via networks. You see an example from transportation. I've been looking at lots of maps like these ones in order to come here today. Graphs that tell you how to move in a transportation system. And we also have a couple of examples from medical imaging. So over here, you see brain connectivity network. And over here, you see an airway tree from the lungs. So this is the tubular system that the air travels through when you're breathing. And there's also a social media network over here. So there's a huge field within statistics. There's another huge field within machine learning that are interested in analyzing graphs and doing statistics and machine learning on graphs. Now, these graphs, they can be very different. I mean, sometimes they are really just dots that are connected by edges and nothing else. But far more often, there's information associated to those edges and nodes. So for instance, here you see 4 different examples of transportation maps. They have different structure, different numbers of nodes. The nodes could have information associated to them saying where they are, so location. Could also be more categorical information, such as, is there an elevator, is there a bathroom, is there a pressbyrån, is there, whatever you might be interested in. The edges could also have information on them saying something about how long does it take to get from one edge to the other, or is it a bus, is it a metro, is it something else, is it a horse? So models should be able to take, or at least we like to create models that are able to take these different types of information into account at different levels. Now, if you look into at least the machine learning literature, I'd say probably 90% of it is about classifying graphs. And there are many reasons for that. One reason is that there are lots of data sets on the internet that you can just download that are set up for doing that, so it's really easy. Another reason is that it's also methodologically relatively easy. So most of the methods that we use, need a representation of the graph in some level. You need to encode it somehow. And if you just want to classify your graphs, then all you need for this encoding to do is to keep your classes apart. You don't have to have similar graphs next to each other. Usually we strive for that, but you don't have to have it in order to have a good classifier. You just have to keep your classes apart. And similarly, if you want to do a regression where you feed a graph into the system and you get the number out saying, I don't know, this is the particular chemical property of a molecule, or this is the age of a brain network, or the person whose brain network you're looking at, well, then all you really have to be able to keep control of is, the order associated with this variable that you want to predict. And everything else could, in principle, be mungled up, and it wouldn't hurt your performance. But if you want to have not just graphs in, but also graphs out, you need to preserve far more information in these intermediate representations. In particular, often we want to be able to interpolate between graphs because lots of statistics and lots of machine learning essentially consists in interpolation. So meaningful interpolation is a really basic thing to ask for in a model like this. And that's where most of my interest lies and has done for a long time. Now, for most of my talk, I'll be talking about work done by a PhD student that I co-supervised, Anna Calisano. She was at the Politecnico Milano, but she spent probably a year and a half with me in Denmark. She was there during COVID when the Italians couldn't go anywhere, and she stayed in Denmark and worked with us. That was really nice. There's also her real supervisor, Simone Vantini. So this is collaboration with them. And in this work, we took on a so-called geometric statistics type of view. And here the philosophy is, well, if you're interested in a particular type of object, let's say hippogriffs. Do you know what hippogriffs are? They are characters from Harry Potter. They are these horses with wings. They're not really horses, but they're animals with wings that can fly. If you're interested in hippogriffs or shapes, brains, trees, your favorite type of thing, faces, anything. If you're interested in one thing and you want to be able to interpolate between these things in a meaningful way, well, most things are actually not behaving in linear ways. So typically what you do is in some way or another, you build a meaningful geometric space of these things, such as hippogriffs, and you often endow the space with a geometry such that you can define lengths between objects and lengths of paths and look for shortest paths as an interpretation of least complicated paths. And typically you would use those geodesics or least complicated paths for interpolation. And you can also use these geodesics to define and compute statistical properties of things or hippogriffs or something else. And that's what we're going to do in the first part of the talk. So as a prelude, I'd like to just say a little bit about how this is usually done on Riemannian manifolds, because that's a relatively mature research field that's been around for longer than I have. So how many of you guys work within geometry? Some of you do. I'm sorry if you are going to be bored. And I'm sorry if my explanation is too shallow for the rest of you to feel up to speed, but I will do what I can. So a Riemannian manifold, well, think of it as a nice analogy is a surface. So like a rubber surface that's been stretched in various ways, but it hasn't been broken. If you look at it locally, it looks like a Euclidean space. In particular, you can define a tangent space. For the manifold to be Riemannian, you define an inner product on this tangent space so that you can compute inner products or dot products, or an analogy to dot products. You can, in particular, compute norms or lengths of vectors. And via these norms, you can define distances within the tangent space. And since the tangent space is an approximation of your manifold, very, very locally, those distances also give you a measure of length on the manifold. So just like you would in Euclidean geometry, you can integrate these very, very small tangential distances in order to get distances on the manifold. And assuming your manifold is sufficiently nice, you will also have geodesics that are locally distance minimizing, and you can use those to interpolate. In particular, on this manifold, typically you will have what's called exponential and log maps, and they map back and forth to the tangent space. So if you fix the point that you really like, there's a reason why it's called mu here. If you're doing statistics, typically you'll look at the mean, or at least the local best approximation of the data that you're looking at. And then you can map all your data into this tangent space via these log maps. So what the log map does is it looks at the direction that the geodesic from your base point here, and to each one of these data points, looks at the geodesics, looks at its direction, and that direction is the vector that you want in the tangent space. Then you just follow that vector in the tangent space as far as you would have followed it, or the geodesic on the manifold, in order to get to the point, in order to find the corresponding point in the tangent space. So basically, you have your surface, you have a tangent space, you wrap your geodesics onto that tangent space in order to project your points onto the space. The tangent space is Euclidean. So in there, you can do all those things that you're used to being able to do with regular vectors. And that's something we want to take advantage of. You can also go the other way. So if you have a base point in a direction, that will also define your geodesic. So you can march along that geodesic again in order to map from any point on the tangent space and onto the manifold, assuming you're not going too far. So yes, we have these logarithmic and exponential maps which locally linearize the manifold. We have this exponential map, and because, well, it's diffeomorphic when you're sufficiently close to your base point, and it preserves distances to your base point. So here I've written it with P to be general, but in general, when we're working with data, we usually use the base point that is the mean of our data. And you preserve your distances to the base point, and additionally, straight lines through this base point in the tangent space are mapped to geodesics on the manifold. So straight lines in the tangent space are going to be equivalent to geodesics or straight line-ish things on the manifold. Now, the way that people used to do statistics on manifolds is to map all their data into the tangent space and do whatever they used to be doing in Euclidean spaces, compute their statistic, and then move or project stuff back onto the manifold. So you use your exponential map to move to the tangent space, compute your favorite statistics. For a long time, people were doing principal components analysis for various applications, and then moving this back onto the data. And this was really popular still in 2009 when I started working with these types of things. And what people would get out of that is they would make these really, really nice figures where you could see how, for instance, shapes of organs in the body were changing as you moved along these principal components. So you could see how they were capturing different types of variation. And I think this is one of the reasons why it was so popular. They looked really nice, were somehow very, very explainable. Now, in more modern modern manifold statistics, people prefer intrinsic approaches, because one of the problems, maybe you can still see it here, one of the problems with this tangent space approaches is that while they're really nice, they're easy to do, when you move far away from the base point, your pairwise distances, they are not preserved. So while the distance to the base point, so the distance from the base point to every one of my data points, this is preserved. But distances between data points, they are not. So when I start doing statistics in here, for instance, if I fit a line, I compute my favorite principal components, or I do regression, I do whatever I want to do. Well, it's going to be a bit wrong. And the farther my data is from this base point, the more wrong it's going to be. So what people then like to do instead is to try to measure these errors or these residuals within the manifold, so with an intrinsic distance. And then there are lots of generalizations of the usual linear methods where you take lines and spaces and try to replace them with geodesics or geodesic subspaces or things like that. But I want to talk about graphs. And they're a little different. So let's first talk about how one might represent graphs. And it turns out, both within statistics and machine learning, this is one of the most common ways to represent them. If you have a graph, you can represent it by its adjacency matrix. So you encode nodes along your columns and rows. And then you encode your edges within the off-diagonal elements. So if you have an edge between node 1 and node 2, well, there's a 1 over here. If you want to make a directed graph, it's not, then the matrix will not necessarily be symmetric. So if you want to have a directed graph, maybe you would have a graph pointing from 1 to 2, but maybe you wouldn't have one back from 2 to 1, in which case you'd have a 0 here. In my talk, all graphs will be symmetric, and all you will, in principle, you could get away with just looking at the upper triangle. Now, so in the example here, I've numbered my nodes. I have 1, 2, 3, 4, and you can see I have an edge from 1 to 2. I have one from 2 to 3, one from 3 to 4. I do not have one between 1 and 4 or 1 and 3, etc. Now, this is a fine representation. It will allow you to encode this thing, but in principle, I could number my nodes differently. I would get a different matrix out. So, I can't just take my matrices and go ahead and analyze them like Euclidean objects because, well, then I won't be taking these different ways of encoding them into account. And my result will heavily depend on how I decided to number my graphs. So you can build a graph space by incorporating all the different ways that you could number your nodes and let them form an equivalence class. We can do that using the language of group actions. So you can consider the permutation group acting on your representation of the graphs. The permutation group just consists of all those permutation matrices that will swap your nodes or the order of your nodes. And basically what happens here is just that the set of all of those different ways you could order your nodes, it becomes one point in the graph space. And within such a representation, it's easy enough to accommodate graphs that have different numbers of nodes because you can just add a little dummy node and then inside the adjacency matrix, just put zeros both on the nodes and all the edges connecting to it. And it's also easy to extend to vector valued node and edge weights by putting, instead of just having a number on each input in your adjacency matrix, you can stick all vectors there. And in principle, you could have categorical labels there as well. There's no reason why you couldn't. Although for what the rest I will do, we will not do that. Now, there's been a lot of work on doing statistics in such representations. The first one that I know about is from 2009. It's actually a very nice piece of work. And then it was sort of picked up again a couple of years ago within statistics. And our work falls into this line of research. Now, what's a bit funny about this way of building a graph space is that when you take this quotient, you actually start to mess up your geometry in ways you might not immediately realize. So you have this graph space, and you have this X, which is just all of those adjacency matrices, and then you have this group, let's call it T for simplicity, which acts on the space, and then you form this quotient, which consists of the set of equivalence classes of adjacency matrices, or the set of graphs, if you like. Now, what you should think about is happening here when I have an element T acting on a graph representation X, is that it's just permuting the nodes. So that's exactly what's happening every time you see T dot X. Is there's a T that's permuting the nodes inside this X. And there's a very natural way to move distances defined inside a top space X or a total space X and move them onto a quotient space with respect to a group, which is to just look at the minimal distance that you can have between two elements of those equivalence classes. And because it's a group that's defining these equivalence classes, it happens to look very nice like this. So in order to find the distance between these two equivalence classes of adjacency matrices, you find the permutation of nodes in one of them that brings it as close as possible to the other one. So in other words, you're doing a matching between the two graphs. You're doing the matching that minimizes the distances between their adjacency matrix representations. You can show that this graph space is a geodesic metric space in the sense that any two points in the graph space can be joined by a continuous curve that is length minimizing, but it's not a manifold. So in order to talk about things like curvature in the space, we've been using a well-known theory of curvature for metric spaces, where you talk about what's called cat0 or cat kappa spaces. So a cat0 space is a metric space in which geodesic triangles are thinner than their comparison triangles in the plane. So what on earth does that mean? Well, if you have a metric space that is path connected, well, it's a geodesic metric space, well, then you can take any 3 points, connect the points by 3 geodesic segments. So that's what you see up here. And then you can make what's called a comparison triangle, in this case in the plane. So that's just a triangle where all the lengths are the same as in your geodesic triangle here. Now, what you can do then, when you have this comparison triangle, you can move along any edge in your geodesic triangle, and look at any point along that edge, and find a corresponding point which is equally far along the corresponding edge in the comparison triangle, measure the distance to the opposite corner. And as you can see, like when your triangles look sort of thin like this, that distance is always intuitively going to be shorter than the corresponding distance over here. So, I'm sorry? Ah, that's true. Yes, it's smaller than or equal to. You're absolutely right. No, so the definition of the comparison triangle is that the length should be the same. So maybe my drawing isn't accurate, but it is supposed to be the same. So you define this notion of curvature through this cat0 property, and you end up saying that, well, if you have this cat0 property for any like anywhere in your space, then it has non-positive curvature. So if it is locally cat0, then it has non-positive curvature. Now, in the same way, you could define curvature bounded by other numbers than 0 by using comparison triangles that have other curvatures. So these would typically be either spheres. So if you use a very small sphere, you get bounded by a very high curvature. If you use a larger sphere, you're bounded by a lower curvature. If you use a hyperbolic sphere, then you're bounded by some negative curvature of the hyperbolic sphere, hyperbolic plane, sorry, etc. And in this way, you can define curvature that is bounded from above by various numbers. And well, if you have a cat0 space, then all pairs of points have a unique geodesic joining them. And the same thing holds locally in cat kappa spaces where kappa is larger than 0. So if you think about it for smooth manifolds, assuming they have bounded curvature, you can at least locally, when your points are sufficiently close, you can join them with a unique geodesic, and the same thing holds within these metric spaces of bounded curvature. And this is the most important property of them. This is why we care about them. This is something that we like to use. Unfortunately, with this graph space, we get into trouble because the graph space geodesics, they're not necessarily unique. So you have an example here where we have two very simple graphs. You take a graph where, well, all nodes have attribute 0 and all edges have attribute 1, and then you add an epsilon or remove an epsilon from the edges of 1, and add some epsilon and add some epsilon, or retract from epsilon from the nodes. But then you swap. So here the nodes are, or sorry, the edge attributes are kept the same in the embedding, but the node ones are not. So here you have 1 plus epsilon, but you have a minus over here. If you want to interpolate between these two, there are at least two ways to do that. One of them is going through the nodes, so interpolating the nodes, where you get 0 attributes on the nodes. Another way is to interpolate on the edges, where you just get constant 1 attributes on the edges. These have the exact same length, and are minimal. So what you can conclude from that, since epsilon can be as small as you like, we cannot bound the curvature of this graph space by any number. And that means there are lots of the types of proofs that people would typically do within manifolds that are not going to carry over to our setting. And just as a comment, this counterexample is not dependent on having edge and node attributes both. You can create the same thing if you only had edge attributes as well. So what do you do? Well, you can start defining things. Anyway, we do that a lot, either way. And you can define such a thing as a Frechet mean. So Frechet mean, it's a point that minimizes the sum of square distances to all your data points. It's a generalization of the mean in Euclidean space, and it's used a lot in nonlinear statistics. And we can also define it here, but it's not going to be unique because, well, if I have 2 points and I want their mean, any midpoint on a geodesic connecting them is going to be a mean. And I have 2 geodesics with different midpoints. So there are 2 means of those 2 points. And because I can in principle design this close to any graph in my graph space by just tagging on this little structure here at any point in that graph. So anywhere in my graph space, I'm going to have arbitrarily close pairs of points that cannot be connected by a unique geodesic. So again, if I think of this in the context of the theorems I usually want to do, I'm in trouble. And it also means that I'm not going to have, in general, Frechet means unique anywhere in my space. Yes? Yes. Yes, I'm sorry. I think maybe it was too fast. So I use the quotient distance that is inherited from the Euclidean total space, or the space of adjacency matrices. So in principle, I take 2 graphs, I align them, and measure the distance between them. Yes. But thanks for asking. Keep it coming. So, and when you do that, you end up in the situation where you cannot be sure that means are unique. Of course, the examples are a bit constructed. So if you just have an actual sample, there's a good chance they will be, but in general, they're not. Either way, even if they're not, you might try to estimate one of them. Why not? And one of the ways that people are very fond of estimating means in nonlinear spaces is a generalization of stochastic gradient descent. And we know that it works when you have non-positive curvature, but we don't have non-positive curvature. Anyway, the way it works is you start with a random point, then you pick another point and you walk halfway along the geodesic to it, pick another point and walk 1/3 along that geodesic, pick another one, walk 1/4 along that geodesic, etc. If you think about it in Euclidean space, if you cycle through your entire data set, well, you're there, you have the mean. In non-positive spaces, you can keep cycling as long as you want, and sooner or later you will get to the mean. But in our case, well, the usual proofs on convergence for this require you to be able to at least locally have unique geodesics. So, at some point, when you pick your geodesic, it's the right one. But we don't have that. So in our case, we've chosen a different approach, which is an analogy of when in statistics, in geometric statistics, is called generalized procrustes analysis. And basically what happens in this approach is that you start with your graphs, you represent them with their adjacency matrices, you compute the mean of all of those, and then you align all your adjacency matrices. So you reorder the nodes so that they come as close as possible to the mean that you currently have. So you swap some of them, and then you compute a new mean. And then again, you realign all your graphs to your current estimate of the mean, and then you compute a new mean. And because everything that you do in this procedure is necessarily going to lower the error that you measure when you're computing or when you're defining a Fréchet mean, you know that sooner or later you're at least going to hit the local minimum. But it's not clear that it's a global one, and we have no such guarantees. So it depends on the initialization of the points at least. But I align them all at every step. I only showed, at least sometimes I only had one in there, but we do align all of them at every step. But it does depend on the initialization, that's true. I mean, this is the same situation that we have in pretty much all of machine learning today as well. You know, you're dependent on your initialization and you're dependent on hitting some sort of minimum at some point. But at least it converges. It's bound to converge sooner or later, and that's at least something. So, you know, just to convince you that you can have meaningful looking means, in a very simple case where we had a bunch of handwritten letters and of the letter A and encoded them via their the endpoints of the pen strokes and the edges that were used to make them, well, we get a meaningful looking Fréchet mean. And I mean, this primarily shows you that at least it's not going bananas in this simple case. Another case where we are looking at mobility networks in the Lombardia region, we look at them at with different types of transportation and compute the mean over different times at the day. And what we see in particular is that you preserve at least the main sort of signal in the different types of modes of transportation. So if you're going by rail, it's very dense. If you're going by bus or car, it's very, very dense. But if you're biking, well, there are only certain distances that people actually bother to bike. We'll see this example again where we see something more interesting. But so having a mean is one thing, but we like to have a little more statistics. And here we utilize the fact that the Euclidean total space is going to be analogous to a tangent space. So remember, in what I was doing below already, I was picking an adjacency matrix, and I was aligning the other graphs to them by picking adjacency matrices that were as close to my chosen one as possible. And in this way, I can, if I want to look at what happens close to a particular graph, I can take my graph, I pick an adjacency matrix for it, and then I can project all the other graphs into this total space consisting of adjacency matrices by aligning all the other graphs to it. And this defines me something that is similar to a log map as we saw them in manifolds. So what this does is it's just aligning the other graphs to it by picking, you know, the most similar adjacency matrix representation. And in particular, the distances to my base point are preserved, just like they would be in the case of the manifolds. And some people have taken advantage of this to build a principal component analysis within the tangent space, simply by taking all these adjacency matrices, projecting them onto, or lifting them onto the tangent space, computing a principal component, and moving it back down to the graph space. And you can do that. But again, you risk that as you move away from your base point, so the one graph that you chose as a base to align all the other adjacency matrices to, your residuals are going to be distorted because while you preserve the distance to the base point, you do not preserve base or pairwise distances to the other points. So if I'm the base point and I have two graphs, you know, if I optimally align them with my graph, they're not necessarily optimally aligned with each other. So in this sense, I still am not in the situation of intrinsic statistics. So, and this is what Anna started with in her PhD, to try to define intrinsic statistics within these tangent spaces. And what we do in order to do this, and it's actually very simple, is to utilize the same idea that was used for computing means in order to compute these statistics. So we start out, we're trying to optimize over what's called generalized geodesics. So these are, again, projections of straight lines in the tangent space. And we're trying to find a generalized geodesic that optimizes the residuals inside the graph space. So not in the tangent space or the total space, but inside the graph space. And the algorithm is very simple. Again, we start out with a set of representations aligned to a random point, compute the principal component inside the tangent space. But now we're not going to align to a mean. We're going to align our points to the principal component. So we have to choose a dimension, and we usually choose the first one, if you have to choose something. But we align our estimates to that principal component and get, in that sense, a set of new adjacency matrices, compute a new estimate of the principal components, and keep doing this until convergence. And just like before, this does again converge to a local minimum in finite time. And now if we look at these handwritten letters, you can see some of the type of variation we capture within the first one is consistently like leaning towards one direction or the other. In the second one, it's more a rotation in the bottom. And on the third one, it's more on this cross that is varying, or that sort of variation that is captured. And if you look at these mobility networks, well, we see that within the rail, there are some nodes where it's differing. So this is the data here is on different times of the day at different days. And what you can see is that throughout the day, the rail it's pretty active at most times of the day, but there are some nodes that are very isolated. Whereas for private car, everything is active at every hour of the day. Bus is a bit like the rail, and the bike is surprisingly active in the whole day. But there is again some edges dropping off over here or over here. Yes, absolutely. So these are mobility networks. So they essentially count how many units travel between two different parts of the Lombardia region at different times of day. So you see some examples of the data points going into this up here. So there are, I don't know, 15 units or something, 15 regions that form the nodes. And then they've been counting how many cars, for instance. So that's private car. How many cars travel from region this to region that? And encode that as a flux on the edge. And similarly, they count how many bikes travel, how many buses. I think with the bus, it's probably passengers that they count, and the same with the rail. So here we actually permute the nodes, yes. Well, they are fixed, but they don't, it depends, it's a modeling question. So do you want to consider a particular node to have the same role at all times? If yes, then you fix it. But if you're more interested in the type of role that it plays in the network, and you're trying to align the networks based on network properties, then maybe you would not fix it. We'll see an even more expressive example of this later. But it's a question we often get, and it's simply a choice of modeling. You will see different things with different choices. So the sort of information that you would get is, for instance, whether there are particular nodes that are isolated. And you could, in principle, have this node changing at some point. So maybe I'll just very quickly jump to the next example, which is very different, but actually shows a bit the same. So this is a social network of baboons, where the networks represent the grooming or the interaction or association between different baboons. And over the course of time, the baboons change roles. So, it's, of course, always baboon 1, 2, 3, and 4. But at some point, the alpha is challenged and, well, maybe actually kicked out. And then there's another alpha. So one of the baboons that used to not be an alpha suddenly is an alpha and now plays a different role in the social network. So here, you expect the alpha to have sort of a special role within the network. And maybe it's a clear example of why sometimes ignoring the labels that you have actually makes sense. In other cases, such as the mobility network, it's more exploratory. We don't know if we will find something different or not. In this case, in the mobility example, there were 2 regions that were interchangeable within the network, and we could see that in them being swapped during the analysis. But in that case, maybe it's not so interesting. But I'll show you a more interesting example a bit later. But here, it makes a lot of sense to actually allow permuting those nodes because you know that the roles are going to change over time. And let's see if this works. It's probably not going to work now that I'm here. If it works now. So what you see here in the, and again, this is a principal component. So what you see is that there are a couple of more isolated nodes that as you move throughout the principal component become better connected. So the first principal component is somehow moving between being very interconnected and having more sort of isolated baboons. Oh. And in the second one, it's at least with the layout, it's sort of more local densening of the network. And it does not like to show the movie. You see it within those nodes that are more local within it, that they get stronger as you move through. So it's more of a clustering type of thing that you see. Now, so those are the principal components, but you can also turn this into supervised models. And here the approach is very similar, defining something very similar to linear regression. Again, we optimize over these generalized geodesics or like projected lines, but now we are minimizing the residuals between the data and the predictions rather than projections onto the line. And it's the same type of approach as before. You start by aligning all your data to a random guess. You compute your regression, then you realign to the regression line, compute a new regression, and keep going until you converge. And again, we know that we will converge within finite time. Of course, that time could be long. So in practice, there's some sort of a tolerance. But we do know that this should converge sooner or later. And here we had another bus transport example, where we look at bus transport in Copenhagen during COVID. And here, Copenhagen was split into different regions. And again, we studied the fluxes between those regions, in this case, only with bus. And I mean, one of the things you can see just by looking at how many people travel in between these different regions, this is what you see in this map. So the intensity says something about how many people cross the boundary of the region. You can see before the COVID lockdown, the first COVID lockdown, there are some regions that have lots of activities, some that have less. Inner city is up here, and this is where you go to the airport. Then during the COVID lockdown, everything is white. There's no one going anywhere. And after the COVID lockdown, it still looks very white, but well, some of the tendencies are perhaps coming back. And we'll see this more clearly. These are the corresponding graphs. And these are actually predictions of the network after regression. So this is again in the period before, during, and after the epidemic. And you can see they look sort of similar. And in particular, this one and this one, they still look fairly similar. But in addition to that, we made an analysis of what sort of nodes were often interchanged while we were doing this analysis. And what we saw in particular when we looked at this is the inner city, looking like this. Before the COVID lockdown, it played a very unique role. So it was never interchanged with anything else, only itself. And the same thing the moment the lockdown was over, but during the lockdown, it was all the time permuted with other things, and it particularly was often permuted with this part. This is where I live. I live in this house here. I live in half of that house, but it's very different from inner city, and it's very special for this region to be similar to inner city. But during COVID, from the perspective of bus transportation, they really were very similar. And again, this is an example of how it makes a difference as to whether you are looking at the actual node and you're really interested in keeping it fixed, and there could be lots of reasons why you wanted to do that, or if you're more interested in the way that the network is built, and you will get different results, and you may want one or the other. And finally, here's an example of from the 2018 World Cup, a match between France and Croatia. And basically, Anna collected how many passes there were between the different players on the field. And again, the different players can take on different roles throughout the match. So you change. I don't know very much about football, but I believe you have a coach on the line telling you to play your game in different ways and have different players take on different roles. So again, it makes sense to not just match a player to himself, but maybe to look at whether they should play a different role within the network. And again, what we see now, we are regressing based on the number of goals that they had scored in total in the match. And what we see is that when there are very few goals, there is a very diffuse topology, whereas when you and you have the density very distributed, whereas when you increase the density, there is a more defined playing pattern, and in particular a very defined single person. So all of this is very classical methods for doing statistics on graphs. And I mean, what's nice about them is that they're very tangible. And we're utilizing the fact that we have this total space where we can easily generalize methods from Euclidean methods, with whatever pros that we have to that. And by using this approach of using the alignment, stepwise alignment or iterative alignment, we actually get intrinsic statistics out, because the distance that we measure, because we are constantly aligning our representatives to the statistic that we're using in our error computations, we actually get intrinsic errors and intrinsic statistics. So that's nice. But there are also limitations, there always are. And in this case, our alignments can be very expensive. So computing graph alignments is generally NP complete. And that means either we rely on approximations, which could be inaccurate, or we accept that it takes a long time. And adding to this, the graph space geometry is non-Euclidean, and there might be more strange properties even of the statistics we are computing that we're not aware of. So for instance, with the mean, we know it's not unique. What about the other ones? Are they affected in ways that we don't understand? And it's entirely possible that they are. So at the end of the talk, I just want to attach a few words to an alternative way of attacking graphs via deep learning. And I had a postdoc, Guan, working on this, where he was working on doing graph-to-graph learning. Now, in his work, graphs are represented slightly differently. They're still represented via adjacency matrices, but he considers them, he also numbers the graphs, and then the representation of the graph will be considered a sequence. So at the first step of the sequence, you just have the first node. So that's what he sees, what you see here. Then you look at node number 2 and how it connects to the rest of the graph that you've seen so far. That's what you build here. Then he encodes it in via the edges. So here you don't have any edges. Here you have one edge to the previous one. At the next step, you look at these 3 nodes. That's what you see here. And again, you encode it via the nodes. So you have 0 nodes, or 0 via the edges. So you have 0 edges up here. And for the next one, you have a single edge to the first one. And then for the third one, you have an edge to the next one, but not to the first one. So that's what you see in the bottom row, etc. So you're sort of adding in graphs one at a time and encoding the connections that they have to the rest of the graph. And this way of encoding it plays together with the so-called can't remember what they're called, an RNN, a residual neural network. No, not residual, sorry. I'll remember it when I'm done. But it plays into this. So at every step here, you're predicting one more node. And you have one branch here for every node, where your first, where you have the edges predicted vertically and the nodes predicted horizontally. So for every one of these columns, there's another node being added in, and what you see here is the encoding of the edges to the rest of the graph. And these are then encoded to a vector in this downstream or the encoding part, and then they are decoded back again to a graph afterwards. And when you do that, you can look at these intermediate representations that you have down here and look at what they look like. You can also have different tasks here. So you have graph in, graph out. And the simplest task you can do with that is what's called an autoencoder, where you stick your graph in and try to predict the exact same graph out again. So it's similar to PCA, only it has these nonlinear components that are hidden in here. And then you can try to look at what happens within these intermediate representations. And in this case, everything that is encoded inside is actually Euclidean. So it's very easy to use your favorite dimensionality reduction tool to look at what's going on. So here, this is the result of a t-SNE that's been used on an intermediate representation. You can see that even though it's just, it doesn't know anything about these graphs other than here's my structure and I'm trying to encode it in such a way that I can decode it back again. You can see that it does actually separate things quite nicely. So over here, you have these things that are sort of symmetric with many arms. Here you have the ones with these sort of spider-looking things, etc. And over here, well, here you have the ones that have some triangles on them. So it's definitely encoding some of the structure. And similarly here, with the IMDb ones, you can see over here you have, well, here you have the very dense and round ones. Over here you have the ones that have sort of multiple angles. Up here you have the ones with triangles in them again. And similarly also over here with a very small data set. So this is trained on very, very little data. It's not a particularly good fit, but you can still see that it's preserving some structure. I mean, over here you have the ones with 2 loops. Over here you have the ones with a particular type of arm, etc. So it's, at least it's producing plots that indicate that it's preserving something. To try to quantify that a bit more, you can try to use those encoded representations. Now these graphs are encoded as Euclidean vectors, and you can run your favorite classifier on them. So what we do is we train this unsupervised representation only with the graph structure, so not knowing anything about them. And then based on these Euclidean representations, we try to do classification using a completely standard multi-layer perceptron, so a very simple neural network for classification. And we train this, at first, in this case on 12 labeled elements. Then we add in some more, 30, 59, 117. They were defined based on percentages. That's why the numbers look odd. And then we compare this in part to a graph neural network that is state-of-the-art for classification, but which only gets to see the same number of elements. So that's this green one that is consistently coming out below. And of course, it's coming out below. It hasn't seen any other data, so it's very hard for it to learn with so few examples. Then we also compare it to some pre-trained versions of the same state-of-the-art graph neural network, which has seen 400,000 graphs. And here you can see, well, this one has an advantage. So the simplest one of those, the light blue one, is just transferred directly without any fine-tuning. And you can see it's basically performing on par with our method, whereas the one that's fine-tuned on the data actually does better. So you can see that what you can see from this is that, I mean, by doing this unsupervised learning, we can perform on par with a graph neural network that has seen a shitload of data, but it's different type of data. So, you know, is that good or bad? Well, at least it means that the autoencoder is learning some latent structure that is useful, because otherwise we would never be able to classify anything. And finally, you can also predict other types of graphs. And here we're using it as a heuristic for graph algorithmics. So we are trying to predict the maximal cliques. And again, what you see on top, is Guan's algorithm. What you see in the middle is a multi-layer perceptron. What you see below is, I believe, it's a GRU. So there are baseline algorithms that you could use for the same. But it seems he didn't include the actual true. I'm sorry about that. So, ideally, there should also have been a ground truth in there. And if there had been, these would have looked very much like the ground truth. But I hope you can at least see for some of these that this doesn't look very much like maximal cliques, yeah? So you can already see from, you can sort of see it over here as well, but in particular for these, you can see that these are not cliques. Here they are, well, this one is not, but this one, they look similar, and here they also look fairly similar. But if you do this quantitatively, you can also see that by actually trying to predict graphs, you can do it. And I like to use that as sort of an encouragement, because what I showed you here, there's no geometry in here. It's just a very naively encoded neural network, and it works decently. But I think there's a lot to gain by actually encoding some of the knowledge we have about graphs and thinking about how you represent them. And some of these things could really benefit from also the work of mathematicians and statisticians. So we've seen these two families of methods where you have, on the one hand, the classical geometric statistics methods working in the quotient space, and where everything works nicely and intrinsically, at least in theory, but in practice, we're going to have problems scaling them up because we rely on these matchings. And we've seen these classical machine learning approaches where you're essentially doing a cheap alignment of the graphs and thereby treating them as being Euclidean objects, but it's actually very naive. And the big open problem is how to marry these sides and maybe have well-defined machine learning that properly aligns graphs or properly takes into account the way that they work. And additionally, a big open problem is also how to take uncertainty into account in these models. So what you maybe will find is some work on doing like generative models for graphs. There's a little bit of that, but it's very, very little, and it's mostly about fitting distributions to distributions of graphs. There's very little on saying, okay, so I have these graphs and I'm trying to estimate statistics on those, or how certain am I about this part of the graph that I predicted, or that part of the graph that I predicted? You know, if I'm doing an autoencoder and trying to predict or decode graphs, which parts of that decoded graph am I certain about and which ones am I not? We don't know how to do that. So I think there is lots of really nice work to be done out there. And we would really benefit both from having statisticians think about how to do it properly statistically, and also having mathematicians think about how to properly encode the geometric parts. And I hope you will join me on that. Thank you.
Okay, thank you very much for the nice talk. And let me ask, are there any questions or comments?
Thanks for your talk. I was wondering whether expander graphs could appear in this framework.
I don't know, what are expander graphs?
It's just a sequence of finite graphs, which are well connected, but very sparse.
So what do you mean by well connected? It's like there are no isolated nodes, or?
Yeah.
Yeah. I mean, so one of the things that we're seeing within the, I didn't tell you, but one of the things we're doing in order to get this to work well is that we are actually, we're not aligning graphs, we're using a depth first ordering to get sort of a poor man's alignment. And if you have graphs that are sparse, I might expect that to work even better than if they're not sparse. Of course, it depends on in which way they are sparse, but if they have these sort of long structures, I would expect something like that to work well. So maybe they are some of the ones that would be easier to get these things to work on than the more dense ones where alignment is harder. I don't know if that helps at all.
It was just, yeah.
Mm-hmm.
Curious question. Thanks.
But it's not something I've looked into in particular.
Okay, are there other questions?
Hello, yes. Thank you for the talk. I wanted to know what happens to the geometry if you use directed graphs?
What happens if you use directed graphs? So in principle, all the geometric properties, I believe, should carry over. Why don't we take a look? So we have a statement in the paper that it carries over, and I've checked it at some point, but let me make sure that everything I said here, that I feel comfortable about it. I mean, so basically, most of what I told you about directed graphs was things that don't work well. And I'm pretty sure, unfortunately, that still holds. Yeah, so if you put directions on these edges, the counterexamples would still work. So the things that don't work, they still don't work. And if you think about the things with the distances and things being geodesic, etc., that would be here. So even if it's directed, you still have a quotient space with respect to a finite group. And that is where everything comes from. It's all very established geometry. And that works out fine. But I think, you know, yeah, all the standard nice things you would still have, and all the problems, unfortunately, you would also still have.
Okay, thank you.
Okay, another. Oh, yeah.
Right. So there's a subject called topological data analysis, where
Yes.
the input are symmetric matrices with 0 on the diagonal, and let's say maybe positive values, up to, they look at the space of such matrices up to exactly your equivalence, up to your operation.
So is this the birth depth diagrams that you're talking about?
I'm talking about the input, about I think about this as a distance space.
So, I mean, so for topological data analysis, you can in principle have anything with a what do you call it, like a perturbation on it, right?
Well, no, the input is literally the input. You can think about the input is a symmetric matrix with typically with 0 on the diagonal and positive, non-negative values. Okay, and up to, those are this is not, you know, up to equivalence relation exactly what you wrote. That's the input, and that space, at least, you know, studied by the CDA people, as you noticed, it's very complex. But the way they try to analyze that space is via constructing various kernels. You know, you maybe kernels related, you know, you think about this as a space, you maybe construct Vittori-Rips complex or Čech complex on this. You really think about these, you know, these elements of your matrix are distances, and you assign some geometric objects and maybe construct homology and then think about this as a kernel. So you go to spaces where you can perform, for example, means and where expected values.
Yeah. So,
but maybe I want to make a comment that one thing is that it's much harder to perform these to understand this when the matrix is not symmetric. Like symmetry of the matrix is like crucial there. It becomes like considerably, I mean, you can sort of formally do it, but things become considerably harsher, even from computational point of view. Things becomes, things becomes very fast, unstable, for example.
So I think I know topological data analysis from a different angle than you do, because I'm used to the object of being pretty much anything. But in terms of kernels, so I also used to work with graph kernels many years ago. And at least the way that we would approach them then is we would take our favorite parametric kernel. So you have pairs of graphs. And you have a kernel on those that gives you some number out. Let's say, let's just call it n. But then, there's somehow implicitly, if this is your graph space and you have your graphs sitting here, there's implicitly a Hilbert space, reproducing kernel Hilbert space somewhere where you have this implicit embedding of your graphs. And then what the kernel does is, it defines various machine learning operators that are implicitly working within this space, but formulated in terms of this one. So in fact, you were just typically right. Sorry. It would be the inner product in the RKHS, looking like this. Sorry. At least back then, we'd have support vector machines or other things working in here, or hypotheses tests based on means computed within here, etc. But I'm not sure if that is what you mean, or if they're using them differently.
That's exactly what I mean. And like I think about topological data analysis. I've studied the space of various kernels, not just one kernel.
Yeah.
The space of various kernels. So you could sort of have different kernel and calculate different mean. And these means would reflect some part of geometry of this complex space of symmetric matrices up to this relation that it's very hard to comprehend directly. Right?
Yes, they're not particularly interpretable. But I mean, so at least when we were doing graph kernels, one of the issues we had was that, one thing is to use this for classification, where all you want out is a number in the end. But if you want to use those means that you compare in or compute in here for anything but, say, a test or something like that, you actually want to have a graph back out in the end. You lose a lot of that information when you go in here, at least with the graph kernels that I know. I mean, they would typically be based on either counting appearances of particular subgraphs and comparing them between the graphs or something like that.
Yeah, so typically an average of some of these objects will not be that object. Right?
Yeah. Yeah, exactly. So if you compute averages in here, there might not be anything up here that actually maps to that. So they were very powerful for classification. I think for graphs, what killed the graph kernels, right? They didn't really die, but when neural networks took over, it was primarily because they could compute or they could train on larger data sets, and at some point that becomes an advantage. So for the kernel, you need to compute the kernel matrix. You're always n squared, with n is your number of graphs, and at some point you can't do it anymore. Whereas with the neural networks, you can feed them one at a time. But I really loved working with graph kernels back then. It was very nice and algorithmic, and yeah. But I'm not familiar with what should I look for if I want to look at this use of multiple kernels. That's not something I'm familiar with in TDA.
Yeah, we can talk about after.
Yeah.
Are there other questions? Yeah.
Hey, just a follow-up question from Isaac's question. Would it be a misconception if I think of directed graphs as like a already included in this because we have a weight associated with each of the edge? So what if I incorporate that direction as just another component that's plus or minus? But are we losing some manifold structure when I picturize the direction of the edge being included in the weight?
So I'll just jump back here. So the way you would encode a directed graph is by, no longer requiring that these adjacency matrices are symmetric. So if your graphs are undirected, then your adjacency matrix will be symmetric. But if you have a directed graph, then these might be different. So either you would have edges going both ways with different numbers on them, and then you just have different numbers on either side of the diagonal, or you could also have one of them being 0 in the sense that there's only an edge going that way and not the other way. And because you can encode them up there, you don't lose whatever structure you have, I believe, but yeah, it's just a little different.
Thank you.
Thank you. Maybe one last question, if there's any. Otherwise, maybe I had one question. Like you looked at this quotient by Sn, the action of the permutation group, and
Yes.
If you encode graphs as like labeled, then there are other natural actions one could consider of either smaller or bigger groups. Is that anything that is relevant in modeling?
Well, I'm sorry, I
You
didn't get
could
it.
look at either smaller groups of NSE,
Ah,
like
yeah.
subgroups where you only allow yourself to permute some parts of the vertices or in certain patterns, maybe, or at bigger groups where you say like, well, I mean, since I'm in this formalism of weighted graphs, I can right away do very weird operations, like, so to say, rotating certain weights. Is it anything that appears in modeling? I wondered.
It's something we considered because we couldn't really work with the permutation groups. Graph matching was really hard. And then, once you move into a practical application, I mean, let's say you were looking at the airway trees of the lungs. I mean, you don't need to consider matching the nodes on the left-hand side with the ones on the right-hand side, perhaps. Well, again, it's a question of modeling, but you could decide to say, some of these graphs, they're clearly going to be matched either this way or not that way, or they're just clearly there's just clearly subgroups that are going to be matched together. And then you could try to split it up into subgroups. It's something we thought about, but we didn't really know how to do it. So we never explored it, but we discussed it certainly. And I think it's something that could work in practice. I bet a lot of graph matching actually works that way.
I'm not a computer scientist.
No.
This was mathematical curiosity driving the question. Yeah.
Yeah. No.
Okay.
I bet it's already happening within that community.
Interesting. Let me check quickly whether there's anything on the internet in chat here. Not that I see anything. So then we have no questions anymore from the chat. Then I think it's a good moment to thank Åsa again for her nice talk.
And thank you for sticking around for it.